Okay, so let's talk about hyperbolas. So remember last time we drew a connection between the ellipse and the circle? Well, there's also a very strong connection between the ellipse and the hyperbola. Although if you looked at an ellipse and you looked at a hyperbola, you'd probably say these have nothing to do with each other, but they're actually much more closely related mathematically than a person might assume. And even looking at the formula kind of gives that away. If you look at our formula for the ellipse and you look at our formula for the hyperbola, at first you go, wait, isn't that the same formula? And if you look closely, the plus in our ellipse formula has become a minus in the hyperbola formula. So that's the only difference between the formulas. So the h and k play the same role as our previous conics. It's going to give you the center of our hyperbola. So we're going to do this. We're going to play the same game that we played with ellipses. We're going to take the a squared and take the square root, and that's going to tell us about a horizontal distortion. And then we're going to take the square root of b squared, and that's going to tell us about a vertical distortion. But it's going to take a little bit more of a framework to construct our hyperbola from those values. But I'll show you how to do it. It's pretty straightforward. And the good news is, in your lifetime, you're going to graph very few hyperbolas anyways. It's one of those things where you graph them just long enough to understand the hyperbola and how it works. But in reality, you're going to use Desmos or some type of computer in order to make a nice hyperbola for you if it's ever important that you need to make a hyperbola for an important project or something. But like I say, the first few times you do them by hand because that's how you get to understand what a hyperbola is you work on those problems by hand, and then later you go, okay, I'll let a computer do it now that I know how it works. So let's dive in. So let's jump into Desmos. So just like before, we've got a value here. It's in an inconvenient form because it doesn't match that form that we just saw, the nice convenient form that we like to deal with hyperbolas. That's okay. We'll play our completing the square game. We'll get this thing in the right form, and then we'll go from there. Oh, and by the way, this is the approximate shape of a hyperbola. We'll look at them. They can also, if you take this and rotate it 90 degrees, you can get hyperbolas that look like that. So whereas this one kind of opens horizontally, left and right, it's kind of doing this kind of a thing, you can have them go up and down as well. They can do that. It just depends on that formula that we're going to look at. So let's jump into the problem. And we want to go right up here. And this is the formula that we want to work on. This is our hyperbola. So, we're going to go through, do completing the square on the x's. So get the x's together, get the y's together, perform completing the square. That's what we're going to start off by doing. So you can see, first thing I did, I got the x's up front, I got the y's in the middle, and I got that constant term to the other side of the equation. So it's over there on its own. So that's step number one. Then we're going to do, just like we did for ellipses, we're going to factor out the biggest coefficient that we can from the x terms. So in this case, that was 4. And then we are going to factor out the biggest thing we can from the y terms, and in this case, that was 9. So see, I factored out the 4 from the x terms, I factored out the 9 from the y terms. Okay, now we're going to do the completing the square step. So just like before, I look at my 4, half of 4 is 2, 2 squared is 4, so I'm going to add 4 in here. And it's really tempting to just write plus 4 on the right side of the equation, but we didn't really just add 4. That 4 is being leveraged. Right? It's kind of like a lever where you apply a little bit of force, but you get a lot of force as a result. That's what we've done here. We've put a plus 4 in here, but it's really being multiplied by this plus 4, which is leveraging it, making it a plus 16. So to balance that, we have to add 16 to the right side of the equation. Now, what about here? I've got my completing the square for the y terms. So 6y, half of 6 is 3. 3 squared is 9. So I add a 9 in here. And here we have to be especially careful. So I wrote plus 9 here, right? I added, like, my hand on the paper is writing plus 9. But notice that 9 is being multiplied by a negative 9. So even though I wrote plus 9 on the left side of the equation, what I actually did was subtract 81 because this negative 9 is going to distribute in here to the plus 9 and make it a negative 81. So actually we subtracted 81 from the left side of the equation, which seems weird because we wrote plus 9 on the paper, but we really subtracted 81. So that's what we have to do over here to compensate. We have to subtract 81 on the right side of the equation as well. So that's what's going on in that step. It's kind of the same thing we've been doing with completing the square, but we have to pay a little bit closer attention to our steps while we're doing that. Okay, so then we want to go through and we want to simplify things. So basically, I'm going to simplify the right side of the equation. That comes down to be 36. Okay, so then we do our factoring. So that's the whole point of completing the square, is that each of those sets of parentheses is going to factor as a perfect square. So we've got that. And then all that's left to do is divide both sides by this 36 value. So we're going to go through, divide everything by 36. So we divided both sides of the equation by 36. Then we do a little bit of simplifying. Now we're in that form that matches our hyperbola formula. Okay, this one right down here. We've now got it in this form, and we're good to go with that. So we just need to identify. We can see the center is going to be at 2, 3. And then we want to keep in mind, we don't know what these values do yet, but we want to keep in mind we're going to take the square root of 9 to get 3. We're going to take the square root of 4 to get 2. The 3 is going to be in the horizontal dimension. The 2 is going to be in the vertical dimension. So just keep track of those. And while we're here, we sometimes want to talk about the foci. So the foci you get by taking c squared is equal to a squared plus b squared. Those are the foci, which is 13. So then if you take the square root of that, you get the square root of 13. And then we can use those to figure out where the foci go inside of this hyperbola. But let's focus on getting the thing graphed first. So here's our hyperbola. Again, we're cheating. I'm kind of showing the thing, but I want to show you where all those pieces come in. So for starters, our hyperbola follows asymptotes. This thing has asymptotes, and they are oblique asymptotes. They're at an angle. They're not horizontal or vertical, and we can see them right. Oops. So this is so remember that 2 and that 3 that we were looking at? Well, those come into our formula for our asymptotes. And you might look at these and go, that doesn't look like asymptotes. That's because we haven't shifted them yet. So you use your A and your B, that 2 and the 3 value we just got from over here inside our, inside our formula. Remember the 2 and the 3 from this denominator, the square roots of these? So then you come back over here, and these give you the asymptotes, but they're in the wrong spot. Our hyperbola is shifted, but our asymptotes are not. But you know transformations, and we know where the center is, so we go, oh, well, if our center is at 2, 3, then if we shift our asymptotes 2 and 3, then they should be in the right place. So that's literally what we do right here. You can see it's just those transformations we're used to. So it's still the 2/3 x, but now we're translating them, and sure enough, if I do that, look, our asymptotes are in the right place now. Okay, well, that's good. That's helpful. So it's following those asymptotes. And then we've got, we've got our vertices, which we can see are right there. So those are the vertices. That's kind of like the vertex on a parabola, except we have 2 of them. By the way, these shapes are not parabolas. They're more like, if you zoom out, they're more like a V because they're following that asymptote, whereas a parabola doesn't follow an asymptote. It's more curved. So these are more like a V, where a parabola is more like a U. Okay, so you want to make sure you know the difference. So how do we actually go through and graph the hyperbola? Well, you can take those numbers we looked at and create a box. So a lot of times this is the method they'll show you, is you create a box based on those values 2 and 3. So what we do is we draw a box where this value is. So from the center, you go up 2 and down 2. Remember the 2 we grabbed from that formula. And then you go over 3 and over 3, and you put lines there. You create this little box. So you go up 2, down 2, left 3, right 3, based on the values that we grabbed from here, the 2 and the 3 from in here. You create this little box, and your asymptotes should go perfectly through the diagonals of that box. If they do, that's a good sign. And then you just sort of do your best to fill in the red hyperbola, starting at the vertex and approaching your asymptote. It's a little hard to be exact with these. Again, you're probably going to have a computer do it if you ever have one that's important. And then remember the foci we talked about. We had that square root of 13, so we can throw those in there, right? So then we can find the values of our foci as well.